Hello, my name is Franco Amaro, and this is our final project, car doors and aluminum. I contribute to this problem because I knew a person that told me about the aluminum alloys that are now used to manufacture car doors. This is because of the deformations that they suffer nowadays. And then we investigate and came up with a conclusion.
Hello, my name is Gustavo Bonilla. I contribute with the calculation of statistical data collect and the analysis of the results with the help of Minitab software. And we begin with the presentation of our final project.
Hello, my name is Juan Antonio, and my contribution for this project was the researches about temperatures used in the manufacturing process for doors and researches for the different percentage of aluminum used in the manufacturing process.
For the manufacture of car doors, it is necessary to run some tests from the different deformations a car can suffer. This happens because of the environment, car movement, and also accidents that can happen. Nowadays, car uses something to make cars go lighter so they can go faster and spend the less fuel possible. This is because new technology that has been discovered. So aluminum is now an alloy used in cars. Car doors have a small composition with aluminum, and what happens if you change the composition in the metal for them to be more resistant? This is what we are trying to achieve in this project. Thanks to some investigation, we found out that if you change the alloys, maybe you could make a door that can last longer and be more resistant. Doors need to be resistant and lighter. This is because cars are getting more resistant and lighter. Movement is different and cars are getting a lot faster. Doors need body frames for them to work, and these body frames are made with some alloys with aluminum and metal.
Literature review and method. Once we obtained the result from testing, we went to Minitab for use a NOAA tool and see if the two variables, temperature and percentage of aluminum, affects the magnitude of distortion. We also made some box plots. One is for temperature against percentage of aluminum. The other one is the magnitude of distortions against temperature, and the last one is magnitude of distortions against percentage of aluminum. For these problems, we propose two different hypotheses that are going to be rejected or not depending on the results. The first one is there is no difference in the results if the temperature change, and the other one is there is no difference in the results if the aluminum content changes.
In picture number 1, we implement a balanced variance analysis. As a result, we analyze the deforming variability. For the model, we use the temperatures and the aluminum quantity. We can observe that there is evidence that temperature has a significant change in the deformation magnitude because the p-value is greater than 0.5. So the first hypothesis is rejected. Also, we can observe with the second factor that there is evidence that aluminum content doesn't have a significant change in the deformation magnitude because the p-value is smaller than 0.5. So the second hypothesis isn't rejected. In the following two tables, we observe separately the factors versus the response variably, and in the last one, the two factors versus the response variably. And we can conclude based on the results and the method that we follow that there is no interaction between the factors and that the higher the percent of aluminum, there is a greater deformation. On the other hand, the temperature of 75 seems to the best option to minimize the micrometers in the deformation.
The combination of a percentage of 20% aluminum and 75 degrees Celsius is the most optimal answer to this problem. So this is the best solution we got for this problematic. Thank you very much, and these are our references.